renewable energy systems. Okay, tell me about the problem that you started with.
Well, problems with the present time systems inside there, they're not very efficient. And another problem is that when somebody actually has to use any kind of energy in a remote area, it's not readily available. And they want more of that. Customers and individual people who actually like to do this kind of stuff, they're very professional at it. They want to have their own set of energy. They want to have their own energy being produced and consumed by themselves, or they want to sell it to the grid as well. Well, this product here actually does exactly that. It is designed for the consumer. As you can see, we have a solar panel.
Solar panel over here.
These are all demos of the solar panel. The fan is the load, which is our example dummy node. We have this dummy inverter.
Good.
This is the charge controller, basically. Which basically monitors and controls the voltage going into the rechargeable battery, which you can charge with the solar panel or the wind energy or whatever your renewable energy source is. So basically, what we do is that we take a renewable energy source, and then we run it through our system, and then you get energy or electricity. And that is exactly what it is designed to do. And Jason will show you a simulation in a minute. Looking over here at the poster, just a very quick overlay. We have the inverter here, the inverter design. This is the buck boost, which is for the efficiency. And this is the charge controller, which will let you, as I said before, let you control the charge in the battery. Here we have a rough simulation of all the things that we have already simulated, and as you can see, we have a few descriptions, we have issues as well, we have approach to our solutions, and we have future expectations for the project and in the future itself.
So simulation of our buck boost converter. So what the buck boost is supposed to do, it's a more efficiency management system. This is a simulation.
This is the simulation.
Yes.
Perfect. That's a MATLAB.
This is a MATLAB simulation. So the voltage level is at 5 volts right now, and the buck boost will be required.
So when you say 5-volt input, so we're saying this?
That's 5 volts coming from the solar panel. Yeah, it's solar panel. Yeah. So 5 volts coming from this.
5 volts.
It's just 5 volt
power, but
how a solar panel works. The solar panel will, depending on the amount of sunlight coming down, it'll range from about 5 to about say 18 to 20 max.
Yeah.
So anything basically less than 11 volts, the battery won't even register it. Anything higher than 14 could damage the battery. So the buck boost is there as an efficiency system to kind of scale it all down to 12 volts, so you don't lose all that power from the solar panel. We have a switch between the buck boost and the actual battery that won't allow for anything but outside 11 to 14 range.
Usually the theory is if I have my whole roof plastered with solar panels, and say I'm generating, I don't know, like usually, how much would I generate?
You're generating watts.
It depends on how big your solar panel is and how efficient it is. Well, that too, and how much it can generate. It will be rated already. You should know
And
that.
the solar panels being used to charge a battery. Too much will destroy the battery.
Well, all the solar panels are generating the same amount of voltage.
Yes.
But when you have them all combined, you're generating more current.
Yes.
And that can be mitigated through the switch on the charge controller. But the voltage itself will remain constant between 5 and 20 from the solar panels.
Yeah.
So this is a simulation of the buck boost, which is more efficiency management rather than safety-wise. So it's at 5 volts.
Good, 5 volts.
So 5 volts is like the lowest the solar panel will come out.
Current as well? Just voltage?
No, just the voltage.
Okay.
So this is the actual plot coming out of the output. This will be your triangular wave, and this will be your PW or your PID controller. So as you can see, it scales up to 12 volts from the 5 volts. Here's your triangular wave, and it's generating a triangular wave which will be combined with the PID controller. And the PID controller will adjust itself and adjust the MOSFETs here, the switches, until it comes out with a proper signal of 12 volts, and it keeps keeps feedbacking itself, checking and checking over and over again to make sure that the signal's right at 12 volts. So that's what we call boost mode, and that boost mode is off of the 5 volts and up to about 10, 11 volts. So if we change this to something higher than 12, so let's say 18.
What's the limit?
The solar panel won't
you
get out more than 20. 20 is like high max. Yeah, we limit it at 20.
Okay.
So then this is at 15 volts. And as you can see, it goes to 15, drops it down, or 18, it'll drop it down, until it hits 12, and it levels itself off.
Okay.
See, now you think that the voltage that might damage the battery, but because that switch in between, that power won't get to the battery.
Yeah.
But the 12 volts, when it goes down to 12 volts, that power will start to be absorbed by the battery because the switch will allow it through, and it will charge the battery up.
Perfect.
And that goes into the battery.
Your system makes it more efficient for charging the battery.
More efficient.
Highly efficient.
So after the battery, it goes to the inverter.
Yeah.
Okay.
So
Now talk about the inverter.
Okay. So we want to send that DC, the 12 volts DC from the battery into 120 volts AC to run a load from the power for a health. For a load.
Got it.
Okay. So that's the fan that we use there with our load, so for the inverter to work, we used a full bridge inverter. So that means there's 4 MOSFETs, and to turn them on and off, we use a PWM generator. So this PWM generator will generate 4 different signals for each MOSFET. So it'll generate signals for the 2 MOSFETs here, MOSFET 1 and MOSFET 4. Those 2 will be on, and MOSFET 2 and MOSFET 3 will be off. That means the power can flow through into the transformer and out MOSFET 4 into the ground, and then it will reverse it, creating the opposite. So MOSFET 2 and MOSFET 3 would be on. That reverses the current and through the transformer, and that creates the peak-to-peak sine wave inverter. So we had the PWM signal generate the PWM frequency. It adjusts to create the sine wave inverter, which goes through an LC filter out the harmonics from the high frequency.
And after the process is completed, you have...
So I'll show a simulation of the inverter first.
Yeah.
So as you see, it starts off low, but it quickly gets up to 170 volt peak and negative 170 volts. So that gives you that 340 volts peak to peak, which is equal to 120 volts RMS.
Perfect.
All right, that shows the simulation of our system. And then next, our supervisor wanted us to build the project, but we tried building the we actually tried building a square wave inverter first. Building with so these sine wave pulses would be squares. So these are the 4 MOSFETs that create the bridge. And the controller turns them on and off, and it outputs through a transformer to step it up.
Okay.
The way fault was we had problems with switching the MOSFET with the reverse current. Our MOSFETs would start to get destroyed. So we had to use heat sinks to stop them from blowing because they were getting too hot for it to handle. So our simulation was working, but our building the system was more difficult.
Okay. So after inner conclusions, what type of efficiency metrics did you derive? Like this system allows a solar panel user to be this percentage efficient. Did you have any conclusions of that type?
Well, actually we do. Is that we are over 90% efficient with the circuit.
Well, okay, hold on. Let's not confuse. The solar panel itself isn't being modified in any way.
No.
The solar panel
The power
depends on the solar panel for the efficiency of the solar panel itself. Our system will just pull the whole system between the load and the solar panel itself will be more efficient because it's not losing power from the daily cycle of 5 to 20 volts, right?
Yes.
So the solar panel itself isn't necessarily being changed. The solar panel can be 15% efficient, 20% efficient. We're not changing that ratio at all. We're not changing that percentage at all. we're changing is the between factor, the efficiency in between.
In
that
between
and
the load and the solar panel.
itself. Yeah.
And we have a small demo to show you as well.
Sure.
As you can see, this is the demo inverter, and we have the load here. And once we connect it to our battery, we'll start running it. This is how it basically runs.
Perfect.
It's going into the load, and it's
Yeah.
providing you with power.
Good. Awesome project. So usually, you know, I used to think that I have a solar panel, I have a battery. Why should I worry about any efficiency between it? The solar panels are good and efficient. My things are running. But you know, like this opened my eye because I never knew that there could be like efficiency problems in between.
Oh, there are a lot of efficiency problems. There is a lot of heat loss. There's a lot of basically the generation, how the material is used, what kind of material is used, what kind of solar panel you're using. Say that your solar panel generates 15 volts max, and it has some kind of a current that's coming in, let's say 600 milliamps. It will not be as efficient when it's providing that direct current. The DC source, it will not be that much efficient. It will just give you a continuous sine wave, which is probably like, it looks like a messed up sine wave.
Yeah.
So you will need to actually refine that process before you can run your load. Otherwise, your load completely just burn out.
Basically,
So that's why it is.
we're making order out of chaos. That's basically what we're doing.
Good. Awesome project. I wish you all the best. The judges are coming.
Sure, thank you.
Yeah. Thanks.
All right.
Yeah. Thanks.
Thank you very much.
Kyle and Jason. Awesome.